these four regions, and you have this phase-space plot. And in this vicinity here, the solution is stable. So you imagine if you started off with composition of U and V so that you were right here, then it says, oh, G is negative, so that means that the concentration of V is decreasing. So you head down towards this line to where G is 0, so that the concentration stays constant. But you're in a region where F is negative, so U is decreasing, and you run down to this point. And if you do that same kind of of trajectories in this vector space, you find you approach this point. Because where these two null lines cross, both G and F are 0. If both these functions are 0, then neither of the chemicals change in time, and then you're at this steady state. So you have this dynamical phase-space portrait which tells you how the system is going to behave. The interesting thing is that, so if you give it a little perturbation, it comes back to its equilibrium. So for example, this is in this phase space, here's in the chemical space, U versus time. If I give it a little I'm at my stationary state, my stable state. I give it a little perturbation to value A here, so U increases because I move this way. Then, since I'm in a region where U is decreasing with time, I'll see it start decreasing. When I cross this line here, then I'll proceed all the way over to this point here and cycle back. So I'll have like a little bump and a little response, and I come back to my stable state. So in this vicinity, close by this intersection, any perturbation I make will restore me rapidly back to equilibrium. If I give it a little larger perturbation, so I come to this side, I have 3 branches in this nullcline here. If I make a little bump, a little greater, then what happens instead is that the response is amplified. The perturbation grows. Because in this region here, F is positive, so my concentrations increase. And I increase all the ways until I hit the nullcline again. And then, if you just follow through, you come back. So in this case, I make a little perturbation to A, like here, but now the concentration, my perturbation grows until I hit here. Once F is 0, V is my slow chemical reaction, so I slowly decay along here, and then boom, I rapidly jump back over here and come back. So if you just trace through, you go through this. So this is called an excitable response. It's very common in neurological, in neurons, in cardiac tissue. It's a very biochemical type of response. And so this is called excitable media if you have a chemistry that gives you this kind of cubic behavior. Then if instead, see, previously this nullcline here intersects on this first branch. If I move over by changing my chemistry so that the intersection occurs in this middle branch, then I get oscillatory behavior, as in the BZ reaction. And so this is in an actual chemical system showing this in the 2 limiting concentrations, showing this kind of phase cycling. And so what happens here is you go through the step by step. You see that no matter where you start with your initial conditions, you'll eventually run into this system. The system will relax into this, it's called a relaxation oscillator, and will just oscillate forever. And so this is also something we see in neurons. And if you follow the concentration as a function of time, you get a very fast response because U is the fast chemical along here. U is changing very slowly, and then here, where F's not 0, very rapidly, and you'll just repeat. And then, so this is what the theory shows, and this is what the experiment shows. in the two components in the phase space u and v, and then one of them as a function of time. So you get these very nonlinear chemical oscillations. And it depends then, you want to tune then whether you have excitatory or relaxation. Oscillation depends then on where these null-clines intersect. And so that's, the chemists then move that stuff around by doing their magic. So this is a simplified mechanism, but one that they're happy with. Because with these, 15 rate constants, they can model everything that we observe. If you measure the bromine concentration as a function of time, you get all this nonlinear behavior. This set of 15 rate constants and mechanism captures it. Though this, they say, is actually a simplification. There's maybe 10 times more intermediate steps, but this is the minimum model that the chemists will accept. And you reduce it down to these 8 coupled differential equations, which you could solve, and they're mathematically very stiff. So you have to take very, very little time steps because there's very fast processes and very slow processes. And so you have to run it, with the time resolution of the fastest processes. So these are very computationally intensive. The chemistry group is led by Irv Epstein here, and Vlad is doing the mathematical modeling. And in our group, we've had Anatol Zhabotinsky for since 19. Anatol passed away this summer after a brief illness, and so this is the obituary that was published in Nature by Irv Epstein. And so Belousov was a chemical weapons scientist in the Soviet Union in the 50s, and he was looking at, I think, something to do with, well, we don't really know what he was looking at, but he came across this reaction accidentally. And he immediately recognized it as being very interesting, and he tried to publish it, and the peer-reviewed journals in the Soviet Union said it violated the second law, and it was impossible. And he said, well, here's the recipe, take these 8 reagents, mix them in these proportions, and stir, and it will happen. And he said, no, it's impossible. And after a while of struggling with, what is it, JETP, what's the equivalent of PRL, the idiots in the Soviet Union comparable to ours, he just gave up. And so he published it on a mimeograph. So the samizdat, is that what it's called? There were these protests. You're in the Soviet Union, you want to write a book or something, Solzhenitsyn, you couldn't publish it, so people would type it out and then they'd mimeograph it and they'd hand it around. So he wrote one of these mimeograph things with the recipe, and he handed it around, and a number of chemists in the Soviet Union in the 50s, did it, and they were kind of amazed by it. So then, 10 years later, Zhabotinsky is a graduate student at Moscow State, and he's studying glucose metabolism and looking at these kind of reactions. And his advisor says, that glucose metabolism stuff, it's too expensive, we can't get hold of the chemicals. I got this mimeograph that's kind of cool, that shows similar reactions. Why don't you work with that? And this professor of biochemistry had 2 graduate students previously try to reproduce Belousov's work and couldn't do it. But Zhabotinsky is a really good chemist, and he got it working really quickly. He figured out the mechanism. He substituted for the citric acid, which made it really sensitive. That was Belousov's originally component to malonic acid, which made him, and then he identified what was the species that coupled to the light. Anyway, he did a whole bunch of work on it, and then tried to publish it. Nobody would publish it, but eventually he gave I think it was 1968, he gave a talk in Czechoslovakia just before the invasion, and there were a bunch of Western scientists there, and they saw it, and they just went crazy. These nonlinear Sweeney and these kinds of people, and they just really loved it. And then it got popular in the West, and then
it got popular back in the Soviet Union. And by 1980, Belousov and Jabotinsky received the Lenin Prize, which is the Nobel Prize of Soviet Union. And so then in Perestroika, 89, Epstein arranged for Jabotinsky to have a tour of the U.S., and he came to Brandeis, and he spent 2 weeks at Brandeis, and he was amazed that he could arrive in the beginning of his trip to Brandeis, order some chemicals from Aldrich, in the beginning of his stay, and they would arrive before the end. And he asked Epstein, "Hey, can you arrange for me to stay longer here? That's what's like kind of heaven to be able to get chemicals so easily." And then he came back in '91. He never left Brandeis, so he stayed at Brandeis and worked there until his death this summer. So science will be the poorer for his absence. He was a very critical thinker and had a very dry sense of humor. He was a pleasure to work with. Epstein's written a book that you can download legally or buy legally. And, that's really quite good. It's about the only chemistry book I've been able to understand. It has lots of math formulas in it and stuff. So I recommend that. If you don't stir the reaction, and you put the BZ in a petri dish, a few milliliters thick, then these oscillating chemical waves will appear. The blue is the oxidation front. And behind it is a high concentration of bromine, which is inhibitor. So you see when the two rings, the two waves intersect, it kills the oscillation because the bromine, the inhibitor species, is moving into the excitatory medium. And this will just run for quite some time. So what we've done then is we've taken the BZ and we put them in little microfluidic devices. In my lab, we do a lot of microfluidics, so whatever comes into the lab, liquid crystal, boom, we put it in microfluidics. So we don't know why we did it, but we just did it. And so these are the microfluidic drops in a capillary. The white is oil separating it. And the bromine, which is the inhibitor, is apolar. And it will leave the aqueous phase and partition through the oil and communicate with the neighboring drops. The excitatory species, the bromate, is polar, and it stays encapsulated in the drops. So the drops communicate through inhibition. Neighbors want to suppress the oscillations of the other. We added ruthenium, which is a photoactivatable catalyst. So if you shine light of the correct frequency, you'll drive all the oscillators into the reduced state. So you can phase the oscillators. So in the beginning, so then we do, the chemists love these space-time plots. So this is the space axis, this is the time. So you imagine digitizing the intensity across this capillary, but just 1 pixel wide. So just take a line 1 pixel wide. So in the beginning, all the drops are off, so each drop is black. The white is just the oil. You're looking at light in transmission, so the oil is always bright. And then the drops either are bright or dark, depending whether they're in the oxidized state or the reduced state. When they're in the oxidized state, they transmit light of a certain frequency. So we're using monochromatic light to illuminate it. So here you see all the drops oscillate in phase because we've shown this light on that sets them all in phase. And we turn off the light and they start oscillating. But then this drop hiccups. It doesn't oscillate. It oscillates later. And then its neighbors oscillate later. And then its neighbor oscillates later. And you get this defect wave propagating downwards until in steady state, every drop is as far out of phase as it can be with its neighbors. It wants to oscillate as late as possible after all its neighbors. So they adopt this 180-degree out of phase because they want to inhibit as much as possible their neighbors.
Seth?
Yes?
Is the oil lighter in the middle than at the edges?
You mean like here than here?
Yeah.
You see, that's again a sign that this is a real experiment and not a computer simulation. Because in the real world, lights are not homogeneous.
Okay.
So that's again, like sometimes, you have these sleuths in NSF and NIH who go through, they say, oh, this data has been manufactured. So we put that in to show them that it's not. This is the real thing. So keep up those kinds of comments, and that'll identify you as a theorist.
Okay.
But we in the lab appreciate that kind of attention to detail. But yeah, we put that in just to keep those ethics guys confused.
Drop to drop is considerably shorter than the medium.
One hopes so.
Because it looks like in one case.
Yeah. So that's the case, and we'll get into the rate constants later. But yes, that's the case. So, but if you change conditions, there's a certain small subset of conditions where they'll stay in phase. So here you see the drops are synchronized. If you make these drops very far apart, then they just oscillate at random. The periods are different, slightly different from drop to drop, and the phase will be random. But there's actually a dynamical state where they stay perfectly in phase for a long time. This is very hard to achieve. We've only got it once or twice, But it's much more common to get this anti-phase. So the phase space for this is much larger than the phase space for that. So there's at least two different dynamical states. Then you can change what we call 1.5 dimensions. So you make the spheres a little smaller, the drops a little smaller. Then they pack in a staggered fashion. Again, look at the intensity of light along this green line. And after a while, what happens is this drop stops oscillating. It just kind of dies. This drop stops oscillating, it dies. And the ones that remain oscillate 180 degrees out of phase. So it's kind of like this. These guys decide not to oscillate, and these guys oscillate 180 out of phase. They're chemically all identical, but they get together and they communicate and they say, okay, I'll stop and I'll let you guys oscillate, and they just conspire to do that. But they can also do other kinds of behavior. So here, this is beginning in time. They start off, and then they all kind of go into this is called a Turing state, where you have reaction diffusion equations, and you get temporal stationary patterns, even though the chemicals themselves have a time dependence. So two go off and one goes on. Two go off and one goes on. So it starts in this kind of anti-phase oscillations. It will flip over into this other stationary Turing state. So the question is, if the drops like to be 180 degrees out of phase, if they like to be 180 degrees out of phase, what happens on a triangular lattice? So you would expect some kind of frustration because these two will be happy, one in phase, one out of phase, but what does this next one do? Either it's out of phase with this one and in phase with this one, so it's frustrated. So here's an experiment. So we start with the ruthenium light so they're all in phase, and then we let them oscillate, and we look for what kind of patterns emerge in this collective behavior. So if, again, you focus on a region here, and you look at the intensity through these 9 drops here, and you line them up this way. So in the beginning, they oscillate kind of in phase, and then you let it go as a function of time. You see there's this regular pattern evolves. There's this periodic staggering. So they've locked into some kind of phase, and what they've locked into is a system where first all the green ones will oscillate, then all the blue, then all the red, 120 degrees out of phase, is a way of kind of satisfying the frustration in a dynamical sense. So this is different than an Ising model because it's got a complex order parameter. In an Ising model, it's either on or off. Here it's on or off with a phase. And so this is an XY class of models. And so you can satisfy the frustration in a certain sense. So here you see the oscillation starting, and then they begin to synchronize where you go 7, 6, 5, 7, 6, 5, and all the threefold periodic neighbors behave the same way. So that's kind of fun to watch. And what more can you ask from the experiment? So you go back to the chemist, you show them this kind of thing. They like plug it into their computer, and now, so this is for one drop, right? These 8 couple differential equations. So now they say, okay, let's take 3 drops. Let's just add a coupling term where we only let the bromine go back and forth, and then they get this. So they get the 120 degree, and you see they're really happy when they get this very nonlinear, fast and slow response, because that's what we observe experimentally. So they can model this if you couple them. But then you do a slightly different experiment. Here we're use slightly different chemical conditions, and then what happens after time is every third drop turns off, and then the remaining ones oscillate 180 degrees out of phase. So here, if you take the intensity, a space-time plot across these 5 drops, the red and green oscillate 180 degrees out of phase. Then the middle one just decides to turn off, and the other ones oscillate 180 degrees out of phase, but with the 180 degree phase shift, which we're used to. So we drop this pattern, and the conditions are just very similar. So there's a lot of dynamical states here, and it's a very rich system. We also have waves, where you can get propagating waves. This we can't model at all, so perhaps maybe some excitatory species is involved, and this is an air bubble. And then in the vicinity of the air bubble, when the wave hits there, you get this kind of little mini explosion. We don't know. We have no idea what's going on here. And then we have a bunch of tools where we have image processing, where we can go in and we can identify each particle, look at its intensity as a function of time, do histogramming, and do a bunch of analysis. We also have developed a tool where we take the PowerPoint, which usually we use to show you the chemistry, but now we're using PowerPoint to talk to the drops themselves, to show them the presentation. So what you do, instead of having the lens, which is a projector lens, you just reverse it, and then you take the PowerPoint and you focus it down into the sample plane, so that the chemicals can see the top. And so that looks like this. Here we're shining on the bright light to phase it. Then we project the PowerPoint to turn off the bright light in certain regions and at certain times, so we can spatially and temporally force the system. And then, so we've developed this programmable illumination, and here's just a movie of it. Now, when we turn off the light, they start oscillating, and then you get, the ones that respond first are the ones where we pattern. So we can go in space and time and set the phase of these oscillators. Then we can change the topology. These are microfluidic chips where we put them on a square lattice, and then we can fill it with drops. And then now we have systems with 4-fold symmetry instead of the 6-fold symmetry. We can change the spacing of the drops, and so control the connectivity between the drops this way. So there's many interesting and rich phenomena. We understand the system really in details at the chemical level, and we have a sense of the dynamical coupling. But and it's fun and everything is beautiful, but really, is there anything more profound? So I think one interesting direction is to create chemical networks that can compute. And this is kind of interest for neuroscience. Not that we're going to make, octopi or some kind of thing that crawls out of the lab and computes things, but all the neuroscientists tens of thousands of them model chemical reactions that do computation, but they've never been able to build such a system. They have to, grow it from, stuff. And so here, we have control over everything. And so I think this is very interesting, just to really make it real what the neuroscientists are doing. And I think it is kind of important to be able to construct chemical systems that can actually compute by putting in the networks. So up here in this picture, we have not emulsions, but BZ in a network. And then by changing the diameters of the channels, we can structure where the waves go. And then in each of these regions, these would be like the neuronosoma, we can put in 100 of these little oscillators, and then we can have communication, different channels, some that are inhibitory and some that are excitatory. And then we can design networks that could do logic in this fashion. So this was designed by one of our neuroscientists, theoretical neuroscientists at Brandeis. And the way we're making it is using multiple emulsions. So here we have BZ on the outside, BZ on the inside. And in the outside, it's in the excitatory state, where a pulse will set it from oxidized to reduced, but it won't oscillate. And inside, it's oscillating. So we'll have excitatory channels running this way, and then we'll have oil filling these channels, and then those will be inhibitory. So we can have both kinds of synapses in our system. And then the final direction that we're working on is trying to couple this oscillating chemical energy to a mechanical transformation. So this is very biomimetic. This is how biology introduces a function into the cell. You have some kind of cycle, some kind of biochemical clock that runs in this case, this cyclin B concentration, and depending on the value of this is the master clock, and depending on its value, then it triggers some microtubule assembly. And then this mechanical stress divides the cell. And then you continue again. So we're saying in chemical oscillations, 50 years ago, Turing postulated that reaction diffusion equation leads to pattern formation in biology. But that's never been found. There's been very, very few cases where biology works that way. Instead, biology works by having separate chemical cycles, one coupling to the other, a clock that couples to some function. And so we're doing the same kind of approach. We're putting in hydrogels that will polymerize and depolymerize depending on the oxidation reduction state, and so create active matter that's driven by the VZ reaction. So thank you for your attention.
Thanks for the fascinating talk. Do we have?
Well, I guess I will be identified as a serious after this question. So you showed how to model the synthesis dose of Bosinski reaction with just one cell with these two coupled nonlinear equations. Is there a modeling, say, for two cells which oscillate in antiphase, or for three cells, for the phenomenon you showed?
Yes, we just phenomenologically add a coupling constant for one of the species. So we're not doing it at a finite element level. We're doing it as saying you have this, you have your BZ oscillator that the chemists use these 8 coupled differential equations, and then we add additional coupling to for some of the species, and then have a separate oscillator. So we're not putting in space. We're still doing it all at this rate equation level.
So you can do this on a lattice?
Yeah, I mean, it's an abstract lattice. It's just so I can make 10 drops, and then you can define coupling with all the others, and in principle, and so it's not, we're not doing it on a lattice, but you can have whatever topology you want. So we put in, depending on the geometry, then we add different interaction parameters.
But in the experiment, just to understand,
Yeah.
the coupling constant is due by the spacing of the particles or something more?
That's one, the spacing of the particles, but also the solubility of the bromine, the partition coefficient of the bromine into the solution, and its diffusion constant, transport. So it's all those things. Right.
So just, I'm very slow, so just question of clarification. So did I understand you had these droplets which have a certain mechanical species, and then there was some material which refused to be surrounding fluid for one and triggered it?
So it's oil and is a continuous phase, and then you have the Belojob-Jabotinsky emulsions as the discontinuous phase. And then one of the intermediate species, the bromine, can partition into the oil, and so can diffuse from drop to drop. Each drop by itself is going to oscillate, but in the presence of all its neighbors, it either decides to turn off or to oscillate in a certain phase.
And then when it comes in, it lights up uniformly everywhere, or it's so fast that you see it light
So
up?
that's an interesting question. So if the drop gets big enough, you can get waves inside a drop. So we're working in a regime, that wavelength is around 100 microns. So and so we're working with drops that are 100 and less. But we can make, if we go to 600 microns, then we can have waves across the drop. So that was in the microfluidics. Then we have regions, very narrow channels where you don't have the waves. So you can play with space that way.
Is it possible to control the communication, meaning how much bromine gets through?
Yeah.
Or-
So
you
the
can control
chemists,
the
yeah.
strength of it.
So we can tune that with the surfactant, with the separation, and with the number of neighbors. So, and also optically, we can address the system. So that's what makes it so fun, is that we have so many ways to precisely and controllably perturb the system. Or useful, I guess. Fun is the wrong word. Not scientific.
Question back there. I was just wondering if you looked at the effect of drop size, because the coupling constant might depend on it, or
We've looked a little bit, but nothing systematically. And, again, this is experiments. So you start making them smaller, then the contrast goes way down because the path is smaller, and and you make them much bigger, and then they break up. And I mean, we'd love to be able to change it arbitrarily, but 100 is kind of nice.
Are any of the steps in the reaction strongly exothermic or endothermic?
I don't know.
Just wondered if you can use temperature fluctuation as a control.
Oh, it's highly temperature dependent. So this is 3 minutes at room temperature. You go to 60 degrees. You can run it at maybe 100 times faster.
But you don't know whether it's giving off heat or, very certain steps.
Yeah, I don't know the answer. I should know the answer.
Yes. So the Hopf problem in 2 dimensions can be Markov KPZ. So you think you could address some of the KPZ problem from an experimental point of view with the system?
So my ignorance of the Hopf matches my ignorance of the chemistry. So these are like 2 questions that are, just.
So maybe we can talk together.
We're going to have to, because I don't even know what you're talking about. I mean, I'm exaggerating. No, a lot of this maps to the Hopf singularity. I know that. So, I mean, I want to follow up on that.
So one of the remarkable things is looking at this is seems that these patterns, they basically form across the system very quickly. It's not that you have a grain boundary where you have off
180 degrees out of phase here and different 180 degrees out of phase here. It seems like it emerges through the whole picture you show us.
Well, it goes one at a time. I mean, per cycle, it affects its nearest neighbor, and then the next nearest neighbor. I mean, it propagates per clock cycle one neighbor.
I see. That's.
Yeah, I mean, I can show
that's
you
sure.
space-time. Oh, yeah. No, so it's communicating nearest neighbor.
In one clock cycle, it doesn't see
No,
further.
not in these systems. I mean, if we go to 3D, if we maybe go to smaller sphere size, then we can. But in these systems, it's clearly nearest neighbor. That's for sure, the interaction. But we imagine we can increase that.
So this is probably time for us to take our break anyway. So back here at